welcome to my single talk for who were mad enough to stay, and to the newcomers, you will understand. So let's. It's a 20 minute talk, so I will try to be as quick as possible regarding what I want to say. The main thing is that I want to evangelize, the way we can work with genomics today in an interactive manner using something like XPy Notebook, right? So in a few words about Datasets, Datasets is a Belgian company so far, but we're creating also the incorporation right now in the US. We have been accepted into the Alchemist Accelerator program, which is the kind of Y Combinator for enterprise editions. And what we do essentially is that we are evangelizing the way to do data science in production. That means that we are adding the agile methodology in the system, but at the tooling level, not at the let's say the physical layer. And based on this toolkit, so we are really interesting in what we do on data science in order to be able to go from the systems to the data scientist instead of the data scientist going to the data lake, for instance. So I am the gorilla. My co-founder is the llama, because llama are cool, right? They are definitely cool, right? And so we both have a scientific background in math from my side, physics for Xavier. We've done a lot of things. We created our own distributed computing in geospatial and genomics 15 or maybe 20 years ago for him. He's older than me. So I created the Spark Notebook. Who knows Spark here? Okay. Who knows the Spark Notebook? Okay. Good. Yeah, and we are training. This guy is a Perl programmer. And yeah, we've both done machine learning, of course. So the lineup for today, very quickly. So I'm going to talk about genomics data, what it is, why we need distributed data sets. Also, what kind of data representation and storage we might need for this information. We'll take a look at a genomic use case, pretty common, let's say, what we can do with this interactive computation to target this and to solve this use case, and finally, what kind of machine learning libraries you may use with genomics today, but that you might not have envisioned so far. So, genomics data. Who is familiar with genomics information here? Okay, so I can give a few information about it really quickly. So first thing is that it's very fast in production right now. So we are very ramping up, and the number of genomes that we are producing every day, right? And I'm not only talking about human genomes, but everything, flowers, plants, or insects or whatever. So we are sequencing a lot of things, and this is really ramping up. For instance, if you think about a human genome, it's like 3 billion bases per sample, right? And for each sample, we are at least doing 30 to 60 takes, okay? And that means that we have a considerable amount of data over here, right? For one single person. And the idea is that this information is produced not in a very linear fashion, so we don't have the full sequence at once. We have this information split into reads, which are more or less 150 base per reads, okay? So this is already distributed, right? So in the biology, in the chemical layer of this process, they are already distributing the computation, let's say, or at least the measure. And the thing is that only producing the dataset is by itself very important. It's very, resource consuming, right? As I said, so we do 30 to 60, we hope, takes on the sequence. That means that we want to be able to have enough, overlap between the reads in order to be able to, reconstruct one sequence with a higher accuracy. So that means that from this, this mass of reads there, we reorganize them into a linear fashion, and then we compute, statistics in order to be able to say, okay, for this position it's probably this one, maybe this one with this probability. Then we have what we call variant, sorry, and this is the variable position in a population, let's say, right? And this is the information that we generally use because, I mean, this is where the variation is, right? So we can strip down the information to these variants only, and there are 1,000 of them, right? So from the 3 billion, you have only 3 million, for instance, 300,000, variants. So it's specifically it's a genotype which is composed of a variant which for the chromosome at which position and this position we have the alleles, let's say A or C for both sides, and then the genotype is referencing one sample, and then we have the information for this variant, which will be either IC, depending which side you are, for instance. But the thing is, now these variants, we have tens of millions in general, and also for the samples there, we are reaching very, very high numbers. So maybe 10 years ago, we had like 1,000 samples available, right? And now we are reaching the million. So this is where we are going, right? If you think about what's going on in the US, there is this 1 million genomes project that has been started by the President Obama. So imagine 1 million of this amount of information. This is huge, right? And huge for, not huge for nothing, right? There is a high opportunity there. So that means that we have a lot of structured data. So I want to emphasize on the fact that we have structured data. So we know exactly what we have, okay? Yeah, I mean, exactly. But the thing is, even though we know what we have, the description of what we have is done in PDFs. Okay, the information is stored there. It's like RFCs, right? So we have this information, it's described like that. So that means that if you want to know what's going on with the data, so then you have to read this paper, interpret it, and then implement it, right? With a lot of interpretations, as I said already. So that means that these things is pretty much okay for human, right? For humans, but I mean, when you want to go beyond that, when you want to have interaction between machines, then you're not in the right area, right? So in order to go from one side to the other, we introduce the notion of schema. So we extract the exact information from these PDFs, right? And we create an exact schema that we can reuse, share, and make evolving in a let's say sustainable manner, right? With different versions and so on, right? So, and schemas are very good for machines, of course, because this is a protocol. It can be respected by constraints and rules. And a schema looks like that. So it's an Avro schema in this case. So we have a record, and record is composed of several fields that might be other records like variant, or we can have also an area of alleles there, and so on. So we can have nulls as well, which is bad but necessary. But anyway, so we have now types. And this type comes from Adam. And Adam is I think I have a few slides about it afterwards, but Adam is a project from Berkeley, Amplab, and they have defined actually these types for everything related to genomics so far, right? Reads, variant, whatever. But also, the importance of Avro is that they're not defining yet a storage. So you're able to plug in your storage the way you like it, right? But a good way to do it, of course, is to use something like Parquet. Why? Because Parquet is distributed, right? It is schema-based as well. So there is a strong correlation between the schema in Avro and Parquet. And also, this is the most important one for me, you can read and query it efficiently. This is one thing which is very important, that you can read and query efficiently, you know, using the types, and also it's pretty much compact because it's partitioned and the partition are compressed, right? And there is a compression algorithm which is very efficient because actually Parquet is column-oriented, so they are able to compress the data like crazy. And why it's very efficient, why you want to read the data is because generally when you do genomics analysis, you will consume ranges of positions into your data set. That means that you will consume a full data set, but with just only one information into the data set. That means that since you have columns next to the other, and information for one column next to the other on the disk, for instance, you just scan read the disk and you have the information right away. So it's very, very efficient. So you can load multiple items And then, thanks to that, you can even load them multiple times, which is not really easy when you have a big targzip stored because you don't want to lose too much storage, right? So you cannot really easily recreate and to read it multiple times. So we worked a lot with the One Genomes project. Why? Because the data is open source. The data is put on S3 as big BZ2 file, right? So they have this project that run from UK, and they have sampled many people from different areas in the world, and they condense everything into Cambridge somewhere. They did it in Cambridge at the end. But the information is very available open source, so you can consume the way you like it. It's on S3. As I said, as BZ2 file. The thing is that since you have BZ2 file, right, you have to download it. No, first you have to find it because, to be honest, the folder is a mess. So of course you have the first data, but then they made some transformation and then some analysis on that. Then you have a mess of folders, and then you have to find your information. And more or less, moreover, there is also some delta increment, so they are adding new data sets in different folders, so it's very hard to find. But anyway, when you have it, you download it, so a few terabytes, 2 I think. Then you unzip it or you unzip it, so it takes quite a long time, hours actually. When you have it uncompressed, you can load it, then you can convert it in Adam, for instance, you save it, and then you can load it in 1 minute. Okay, so from hours, using the right tools, right, you can load it in 1 minute, the same data set. Okay, and regarding the size, we have a raw file for part of information which is 152 gigs, right, and it's compressed with the same information, but clear, right. We have 70 gigs. We have reduced by 2 the size, but raw data is not readable. The Adam data is readable like this. I mean, you don't have to do anything. Also, we had 33 parts for the raw data, of course, 1 per chromosome. And for Adam, for our test, we created like 10,000 partitions. That means if you want to use that in a distributed manner, you can reach a factor of prioritization over 9,000, if you like. So this is pretty amazing. I mean, and also the raw data per se, when you haven't compressed it, is not even easily distributable because the schema is on the schema. The headers is of course in the headers, so you cannot share the information efficiently. And the PDF that I shown before are not very strict, so they are open to some modifications. So it's very, very painful. But to load it in 1 minute, so what you can do is that you can just use Spark, right? It's Spark A. Right? And it's very good at that. So you take your Spark context, you inject the Adam libraries, and then you say Adam load, you pass the file to that which is on the tree, and you have it. Then you return what? A RDD of genotypes. It's typed. It's not like strings. So if you had read BAM or SAM files, you would have byte strings or byte arrays, or you would have just string. Right now you have a genotype. So you can call functions on that, at least fields. So this is the good thing. So now, from the notebook like there, you can start consuming the data and starting your exploratory phases. The problem is that actually we have quite a number of samples, right? So the data is starting to get pretty huge. And if you want to know if the data is heterogeneous, so if you want to see if the samples that you have are part of the same, let's say, population, right? How to know that, right? In order to know that, so you will start to do some clustering, right? So without the first principle, that means that you want to, you don't want to model the way structures are created into this population. You want to just learn from the information available right now. So you will do in supervised learning. So most of you know Spark, so the interest of Spark here is that you can scale. You have a few layers on top of Spark which are pretty interesting for manipulating the data, like graph processing. This is my preferred, to be honest. Machine learning a little bit as well. You have not only MLA, but you have other ones, and you can also optimize the way the memory is used and so on and so forth, right? It's Spark. Spark Notebook, as I said, so we want to be able to do interactive manipulation of our genomes. Why? It's easy, actually, because you don't know what you will do with the data. You start looking at it, right? So you want to be able to do manipulation of the data many, many times before you just found what you want to do at the end, right? So you have to be interactive and not launch jobs and waiting for it to come back with information like, you can really do unit testing when you do data science, right? It's really hard because you don't know what you want to do to go. You can do it afterwards, but not before. So the Spark Notebook is interesting for that because it's interactive, of course. It's Scala-based, so you will be able to use the power of the types. It has a reactive and playable charts API, so you can have your model trained with a fancy chart showing how good they are, and you can early stop them. It's easy to install because it's only a target zip with no dependencies on the system. And the thing is that you can have multiple people using it without conflict because it has multiple Spark contexts. So each time you launch a notebook, you have a new Spark context. That means one guy can work with the Adam 016 and the other guy can work with the Adam 019, and there is no conflict because they are not sharing the same class path and the same JVM, actually. So there are new JVM spawned each time. It's interesting because then you can have this huge function right there in a cell, right? And it's doing very fancy things, right? It's pretty unreadable. But the thing is that you can split it, right? And you can split it in such a way that you can check with the types what's going on well or wrong, right? So it's mainly manipulating tuples there, right? And you can very easily doing errors. But thanks to the types, you can split it at one time and say, okay, I control enter and I see what type I have, and then I can be helped by the compiler to be able to move forward. And this is the importance. If we get back to a dynamic language, and we had made these efforts to have the types for the genomic information, then we will be losing quite a lot of advantages, of course, of the schemas on the data. So yeah, this is how you would compute frequencies for the alleles, right? So then you can compute it, and automatically the notebook detects that it's a list of double and int, and then it prints a bunch of information. The other plots, you can do radar, you can do parallel coordinates if you like, whatever, but this is the automatic ones. And you see the distribution. That means that most of the variants are shared and then are pretty old, and then the variance probability is decreasing. Distributed machine learning, well, it's important to be distributed. Why and when? When it's easy, it's as fast as possible, as quick as possible, as sooner as possible as well. So why you want to have distributed machine learning is because our data sets are getting huge, multi-terabytes, so we are reaching the petabytes in this area. We have huge models, right? So you are eating a CPU model on one machine, and we want to have distributed algorithms on that. And also, we want to do very large assemble. So we want to run many, many models and assemble at one time. That means you can use the distribution environment to do that. You want interactivity on top of that, otherwise it might take a lot of time before being able to do something great. And at the end, you want to have your results to be service-oriented, right? So you don't expect a geneticist to look at charts at the end. So you want to see generally the raw data in order to be able to hack on the system, let's say, to give the right medicine. So it just is very happy with one number saying the probability. And then, of course, with distributed environment, you can use you can optimize the way you will launch a job thanks to constraints on the infrastructure. So Spark MLlib is one good option. You have these things. I won't go in detail to that. But this is one example to do unsupervised learning. This is the classical k-means, but we do it on genomics data, right? It's 2 lines. You load the data. You prepare it a little bit in order to have right matrix. There I think we used there the Manhattan distance between positions. So you have for a very small space, then you can compute Manhattan distance between points because you can code it CTG as 4 points in the space. Anyway, but then you can very easily compute distance and then compute the k-means, and at the end you can separate population pretty. It does a pretty good job without any optimization. Here you have 3 populations and the clusters, and the matching are pretty good. But the other one that you can use also is H2O. Who knows H2O here? Right? H2O is a very okay. So I have I think, okay, so I just have 2 slides I want to show. H2O, so is there something that you want to look at? Yeah, because I have implemented the whole in-memory MapReduce, but it's very highly optimized for structures in JVM. It looks like that, and you can do it this way. So from SPAR, you can create your H2O context, and from there, you can start using H2O. I recommend you to watch this video. It's my buddy, Xavier, that does it, that presented something at H2O World recently. And mainly, what you could be able to do is run H2O context as data frame on the data, and then you were able to run some deep learning algorithms in 2 or 3 lines, or a few more lines. And it did a pretty good job as well. Right, some takeaways. So write data with a schema, if possible. Work interactively, prepare a big infrastructure for that. Good machine learning, so libraries that you want to use right now, and being able close to production is very important so that you can deploy your work as a service efficiently. That's it. Sorry for burning the timer. Yeah.